Okay, so let me summarize what we have done. Previously, during our last online class, you have seen this thing, how we derived the nuclear reaction rate expression. And the most important fact was that this reaction rate has got most important contributions from very limited pocket range, and that is belongs to the gamma window. Here the cross section is really important. And talking about gamma window, two very important things comes to our mind. One is the peak of the gamma window, this one, and another is the width. So these two things are important. One is peak and another is your width. Okay, now we have derived the expressions for the peak and for the width. I am not going to write it. But you must remember from those expressions that in both peak and in both width, we have got expression which is basically described by the gamma energy Eg and temperature. Right? So they are the most important parameters which basically describe your nuclear reaction rate apart from density and other factors. This is very important. So now what I am going to do, I am again going to write down the reaction rate. Fine. আচ্ছা, এবার দেখো যেটা করছি সেটা হচ্ছে, the first thing that I am doing is regarding the astrophysical S factor, AC, I am just replacing it by the value at the peak, that is the gamma peak. Let me do this. Now as a result, my integration will be solved very easily. Now why I am doing this? Because AC varies very little over the energy range. This is the reason. So now I am writing this entire reaction rate in terms of this density factors, these constant factors. Remember there is a temperature dependence over here, this term. Then here the S is 0, followed by again another temperature dependence but in exponential term. And then finally this term here. Here basically we have got information about what is the width, or basically what energies will be contributing, right? What energies will be contributing to the gamma energy, to the gamma window, this information. So this is contained in this integral. Now if we do this integral, if we solve this, you can check after putting in the various values of this pi, mu, these various constants, that we get this result. Now I have condensed mu into reduced atomic number. Here ZA ZB, again density dependent term is there, S of E0 is there, and finally these are the constant terms, and in this row, the second row, we have got the energy terms and also basically Eg and T. So these two terms again. So this is how I am showing you the importance of the gamma energy and temperature in the reaction rate. So here first column mostly constants, and here we have got the exponential terms along with this factor, and here we have got Eg and T. Now as I was saying, during the evolution, when the star collapses, what basically happens is the temperature, the pressure increases near the core, and as a result your density increase, and if we consider your normal ideal gas, then what will happen? The temperature will increase. However, if the mass is very low, then what can happen is that the core material can become degenerate. That means atoms can get squeezed enough, electrons come out, and the de Broglie wavelength of the electrons, they become equal to that of the interatomic separation. And in that case, when the core material, they start become degenerate, what will happen? You remember the degenerate equation of state. So in that equation of state, there is no temperature. So this means that once the matter becomes degenerate, the temperature will not change, and as a result no fusion will happen. Okay, and we call such quantities brown dwarf and it happens below around 0.08 solar masses, and above that we can have fusion reactions. So basically the fusion reactions are the main source of hydrostatic equilibrium. Now let me talk about the fact that suppose the mass is more than your 0.08 solar mass, then what will happen? As the temperature increases, first which reaction will happen? Out of hydrogen, helium and all that, the lowest Coulomb barrier is possible for hydrogen. So we can have hydrogen fusion reaction. Now after your hydrogen fusion is over, then in the very core you will have only helium and hydrogen will be burning. First it burns in the center and afterwards it starts burning outwards in the shell. So shell hydrogen burning. What happens inside? Inside we have got only helium, right? Now you see, so we have got helium material, high density, but there is no fusion reaction. So who is going to sustain your hydrostatic equilibrium? Because there is extreme gravity which is always there. As a result, helium core will start condensing. Helium core will start condensing, and as a result, even if there is degeneracy somewhere, later on this will be lifted on, and what will happen is that temperature will again start rising. As a result, what will happen? As the temperature rises, density is also increasing, temperature is also increasing, so there is a chance that helium nuclei can fuse. So this means that the different phases of nuclear burning, hydrogen fusion, helium fusion, there is a gap. So it doesn't mean that suppose at this moment hydrogen fusion stops and just after 1 minute helium will happen. It is not like that. There is some gap over there. So this is one important conclusion. Another thing is that we need higher temperature consequently for fusing heavier and heavier nuclei. Okay? So this is the actual scenario. Now what we are going to do is, this all depends on this whole thing, the energy, how much energy we get from this entire fusion reactions. This basically you can estimate here. Basically the nuclear energy rate per unit volume is given by the energy released in the reaction delta mc square into your reaction rate. So this is basically proportional to density square into, this whole thing you can think of it as if there is a temperature dependence. Remember the whole discussion that I have been doing right now. This basically tells you that temperature plays a very crucial role. Right. So let me write the reaction rate as if there is a sort of some temperature dependence, T to the power nu. Then I can write this whole nuclear energy rate per unit volume as E0 rho square. Rho square why? Because there is a Na and B density term into the temperature dependence. Now this equation is an auxiliary equation important for solving the stellar structure equations. Okay, so this is how we do the calculation. But regarding the temperature dependence, how can you define T to the power nu? This means that you have to do a sort of definition like this here. So this is how we define the nu. Log of d log of RAB divided by d log of T. This is how we define the temperature coefficient exponent. And from this you get RAB is proportional to T to the power nu. This is how we do the reaction rate calculation. Next, let me do a homework. I am basically giving you the homework. So in this expression you think that the first line is basically a constant, some constant A into this dependence on Eg and temperature, and you do this and you do this calculation and you really show me, this will be your homework, that you get this value of nu. Of course it will not depend on this constant, say, right? Now, so applications. The first application we are talking about hydrogen fusion reaction basically. As you know, at low temperature hydrogen fusion has got contributions from PP chain, and at higher temperature we have got CNO cycle. Now I have written down this PP chain reaction over here, and again I have just shown you the value for the reduced mass, and I have assumed the central temperature at this value. If you do this, then it's your second homework that you have to show after doing all the calculations for Eg, 4B, kVt, that you get the value of nu 3.84. So this means that the rate of the PP chain is proportional to T to the power 3.8. I'm just forgetting this 4 factor. Similarly, for CNO cycle, this one important reaction is written over here, and you can also check this by yourself that indeed after doing a similar estimate like this over here, you get the temperature dependence nu 19.6. Okay, so this is what we have. Now, let us consider our star stroke. Suppose we have got a low mass star. Then, since the mass is small in the star, I am calling it a star. This means that fusion is happening. Otherwise, I would have not called it star. So, low mass star fusion is happening, but the temperature is low. Right? So, this means that here PP chain is important. It is the one which is giving me the luminosity, the energy. Since the temperature is low, CNO cannot be initiated. Now let me talk about the massive star. Here the temperature is high, and so we have got CNO cycle. Now in this plot I have shown you the same thing, is log of energy generated per unit volume as a function of log of core temperature. Now you can see the initial part PP is there, the slope is like this, but the later part, as the temperature is higher, the slope is more in CNO. This means that the energy you get from CNO is much more, but it comes at a later stage, at higher temperature. So this is what you can take from today's lecture. Any questions?